Number 2 is a type 1 integral because of the infinite upper limit of integration. Now this problem is very similar to number 1, so this should be very easy. And we know that the antiderivative of 1 over x is a natural log of the absolute value of x. Then we use the fundamental theorem of calculus. So we'll have the limit as t, where t represents the area, because integrals are the area below the curve, as t approaches infinity from the left because it's the upper limit of the integration. If it's the lower limit of the integration, we would say the limit as t approaches infinity from the right. Now we'll have the limit of t is the limit as t approaches infinity from the left of the integral of 1 over x dx from 1 to infinity. Then we use the fundamental theorem of calculus. We'll get natural log of the value of x from 1 to infinity. And that will equal to that limit as t approaches infinity from the left, ln of infinity minus limit t approaches from the left, natural log of 1, which then equals to infinity minus 0. Since the area is not finite, number 2 is a divergent improper integral. Thank you for. So for number 4, we have the integral of 1 over x minus 1 raised to the 2/3 dx from 0 to 2. Number 4 is a type 2 improper integral and a bit harder than number 1 and 2. So first we'll look at the limits of integration. So we have from 0 to 2, then we check at what value does the function become discontinuous. The function is discontinuous at 1, so we split the integral into 2 parts. So we'll have the integral of 1 over x minus 1 raised to the 2/3 dx from 0 to 1 plus the integral of 1 over x minus 1 raised to the 2/3 dx from 1 to 2. Now we find the limit of the antiderivative of the given functions, integrals. The antiderivative of the given function is 3 times x minus 1 raised to the 1/3. Using the fundamental theorem of calculus, we'll get 3 times x minus 1 raised to 1/3 from 0 to 1 plus 3 times x minus 1 raised to the 1/3 from 1 to 2. Oh, I skipped an important step, but this would be the same as finding. Um, well, actually, I forgot to find the limit. Don't forget to find the limit when you're looking for improper integrals. So there should be limit as t approaches 1 from the left, and limit as t approaches 1 from the right. Next, we'll get 3 times 1 minus 1 raised to the 1/3 minus 3 times 0 minus 1 raised to the 1/3. Group those functions plus the same thing, 3, well, not really the same thing, 3 times 2 minus 1 raised to the 1/3 minus 3 times 1 minus 1 raised to the 1/3. Group that, then we'll get 3 plus 3 equals 6. So the limit as t approaches sorry. So the value of this improper integral is 6. So therefore, we have a convergent improper integral. It's important to check both integrals unless you get an infinite or non-existing limit, because if one of the integrals are infinite or undefined, then the whole integral is divergent. Thank you for watching. Okay, for practice problem number 2, we have 3 over the square root of 8 minus x, or 3 times 8 minus x raised to the 1/2 dx from 0 to 8. Now, number 2 is a type 2 improper integral because the function is discontinuous at x equals 8. Now we find the limits of the antiderivative, so we'll get the limit as t approaches 8 from the left of the antiderivative, which is negative 6 times 8 minus x raised to the 1/2 from 0 to 8. Use FTC, then we'll get negative 6 times 8 minus 8 raised to the 1/2 minus negative 6 times 8 minus x, 8 minus 0 raised to the 1/2, and that will be 0 minus negative 6 times the square root of 8, which we can simplify to positive 12 times the square root of 2, since we have a finite area, we have a convergent improper integral. Thank you for watching. For practice problem number 4, we have the integral of 4 over the square root of x times x plus 6 dx from 0 to infinity, so we know this is a type 1 improper integral. Now, to solve this, you'll need to know how to integrate by parts, which we haven't discussed in our introduction video. So, I recommend you check our colleague's video right here on how to integrate by parts, and then come back to solve problem number 4. Thank you.